My presentation today was sponsored by the Nickel Institute and AMOA, which are two stainless steel industry associations. And if you haven't found it in your handout, there is a flash drive with over 250 documents on it to help you with specification of stainless steel. So I did want to bring that to your attention. As a metallurgical engineer and material scientist, the way I look at problems is a bit different from many of you in the room. So I wanted to put the arch's stainless steel in perspective. When the arch was constructed, stainless steel had only been available for 50 years. Depending on whether you credit the Brits or the Germans, it was either invented in 1912 or 1913. The structural applications for stainless steel had only been around for about 20 years, with the largest of which had been rebar for the Progreso Pier in Mexico from 1940s. But otherwise, as a structural material by itself, there had only been fairly small applications and very little research. So when the arch was designed, using stainless steel plate as an important part of the structural element, as was explained, there was concern. And so a great deal of research was done by the stainless steel industry, starting in the early 1950s through the 1960s. And that then led to the first standard in 1968, which was AISI, and then an SEI, that became the SEI ASCE 8. There has been subsequent research over the years. There's a Japanese standard, Eurocode 3, has all structural sections, and new AISC Design Guide 27 that came out about 1.5 years ago. I was on the steering committee for that. All of this research was used first, not on the arch, but the Unisphere can actually claim to be the first large structural application for stainless steel. The research was already in place. Of course, the arch was under construction. But it was donated by the stainless steel industry as essentially a piece of advertising. It had stainless steel from every producer, 304 welded together, and is still doing well. Stainless steel has been used in many restoration projects. One of the most recent I'm familiar with is some work on the Acropolis, where they're using a duplex stainless steel for high strength, but it's very common to use it in hidden applications, not just in the very visible means that we see it on the arch. One example of that was the Statue of Liberty restoration. When you put large sections of copper in direct contact with cast iron in a structure where moisture is going to infiltrate, you're asking for galvanic corrosion problems. The designers did understand that, provided for separation, which went away over time. And then there were additional efforts to separate the metals, but there was iron corrosion, which expanded, damaged the copper, and in the early 1980s, they started looking for solutions. The framing, the secondary framing, is a duplex stainless steel, and then the bars that are in direct contact with the copper are 316, which has the same coefficient of thermal expansion as the copper, unlike the original cast iron. There have been many large building framing applications for stainless steel. The earliest were to get stainless steel into the structural design guides around the world. The largest after that was the Canadian National Archives. There are also, have been since the Gateway Arch, many large welded structural stainless steel projects. As Steve mentioned, I have worked on many of these as a member of the design team. And when I worked on the US Air Force Memorial, one of the first things I pointed out was, take a look at the arch. There is no access. We need to provide a means of inspection. So there are loops going up. Each of these spires, if you happen to visit, you will see them. That's 3/4 inch thick Type 316 L plate that was welded together. No carbon steel. So I often get questions about what stainless steel is and how it works. Stainless steel is iron plus at least 10.5% chromium and is low carbon. The name, going back to the very beginning, was stainless, not stain-free. Just want to point that out. It's a rather critical point. You can add corrosion resistance to stainless steel by adding more chromium, molybdenum, and nitrogen. And you can pick stainless steels that will not corrode in a specific environment, but you have to pick the right one. So you can't just say stainless. Formability and weldability is added by nickel. So on the gateway arch, we have a nickel-containing stainless steel. So that meant that if there was a welding problem, that weld could be cut out and re-welded, and it really wasn't a big deal, which was important. There are also inherent differences between stainless steels in corrosion resistance, and you can do a calculation based on the chemistry to determine the relative corrosion resistance. There's a lot more about this on your flash drives, and create a PREN number. That's a pitting resistance equivalent number. I've shown a few stainless steels that are used for structural applications, and you can see the last column is a PREN number. The higher the number, the more corrosion resistant the stainless steel. You can see that 304 is at 18. 316, you're probably familiar with, is at 25. As you go all the way up to those that are in the 40s, those are stainless steels that can be immersed in seawater and not corrode. So there is a wide range. The strength of 304, 316 is essentially the same as that for carbon steel. So in the design of the arch, we were well matched in terms of strength of materials. I showed duplex stainless steels that are sometimes used, as I showed in the Statue of Liberty, for higher strength. They're about double the strength of the carbon and austenitic stainless steels. Steve showed some pictures of the inside of the arch and the carbon steel with very little corrosion on it. As carbon steel corrodes, you get a layered appearance, and those layers actually tend to retain more moisture and accelerate corrosion. Stainless steel, when it corrodes, pits. So it's a very different corrosion process. There has been a lot of work done by metallurgists like myself, and I'm involved in three corrosion projects right now, 2 in the Middle East and 1 in China, where we're doing long-term corrosion studies. But you can take that data from whatever part of the world it is and use those corrosion rates to predict the life of materials. And there's a lot of data available. I'm just showing this for standing seam roofs. It's quite easy to make those comparisons. So when we're looking at construction materials of any type, they all corrode, just as our bodies corrode. It's called aging. They oxidize. So we need to look at the environment. Is there pollution, or was there over the structure's life? What type? Is there salt exposure, coastal or de-icing, and at what level? What are the weather conditions? If you get regular heavy rain and you have a structure that's fully exposed like the arch, then you get natural rain cleaning. And at the top, with wind levels, we probably get power washing levels of rain cleaning, as happens at the top of the Chrysler Building, because that was measured as well. Will there be maintenance? And are there aspects of the design that might cause corrosion problems, like unsealed crevices? And then the type of finish that you have also makes a big difference. Mishandling, as was mentioned, occurred a little bit during installation, can also cause some surface contamination and damage. Since Steve talked a little bit about the studies, and I don't want to infringe on what is going to be talked about later, I wanted to talk very briefly about what humidity means in terms of corrosion. If you do not have salt in the environment, which you would not have between the layers, then you need about 80% relative humidity to have corrosion occur. And we have a time of wetness issue, a TOW, which you might see if you're working with a metallurgist. And if you don't have a very long period of time where there is moisture present, then you can't have corrosion. If salt is in the environment, and in this case I'm looking at 3 salts that are both found in sea salt but are also used for de-icing. We used to just use sodium chloride, rock salt, for de-icing. And when we only had that in the environment, which wasn't introduced until after the arch was built, you had to hit 76% humidity and 50 degrees Fahrenheit for that salt to be actively corrosive. Salts lower the humidity levels at which corrosion can occur, but spring rains would wash most of it away. Calcium chloride and unfortunately sometimes magnesium chloride are increasingly being used for de-icing. When those are present in the environment, then you only need 45 or 50% humidity, and as soon as you're above freezing, they are actively corrosive. In the case of the arch, the highways are some distance away. But if you're working on a project where there are roads immediately surrounding it, finding out what a city or municipality is using is quite important. This is a 1980s US and Canadian corrosion map done by the automobile companies. Ignore the West Coast because that's not particularly accurate, but you can see in the 1980s the effect of de-icing salt and industrial pollution around the whole Great Lakes, well, what was really the heavy industry belt. I also show on the right data from the Salt Association and the fact that we have essentially doubled de-icing salt use since the 1980s. And that has changed the map. If you're working on a coastal project, the US National Atmospheric Deposition Program is a great source of data. This is just for 1 year, but you should look to see what salt exposure is for a location. For stainless steel, this stainless steel inspection, we were looking at a number of different things. First of all, a visual inspection. Is there corrosion or other discoloration? The appearance of the welds, including possible defects and any corrosion around them. Corrosion patterns can tell you a great deal, as can the appearance of a weld, and other visible damage. We went through archival information, and we got 5 weld samples to evaluate. We used GSR, those are gunshot residue kits. TMR has been using them for a very long time because you're able to collect fine particles from the surface that you would not otherwise be able to collect to evaluate without having to do anything destructive. Just as the police can determine if someone has a gunshot residue on their hands or collect fine fibers. Now you can use a scanning electron microscope to determine exactly what those are, which is what we did. We also looked at the finish, which will be discussed later, and there were cleaning trials. So in the 1960s, the stainless steel came from 2 producers. There were 886 tons of 304, and they came from what was then Eastern Stainless, which is now part of Outokumpu, and what was then a division of US Steel, which is now ATI Allegheny Ludlam. Having friends at both places, I talked to them about technology at that period. The first AOD argon oxygen decarburization furnace in the United States was not installed until 1974. AODs allow removal of a lot of impurities. It was not possible to make low carbon stainless steel consistently until those were introduced. So we had to assume the stainless steel on the arch was not going to be low carbon, which introduces the possibility of things like weld sensitization. It also meant it was likely to be high sulfur, and high sulfur also introduces some potential corrosion issues. So in order to understand what we found on those GSR kits, it was important to look at what historically had been around the site. And here you can see the highways and the distance from them, but we took a closer look, and I did want to point out that if you're working specifically with stainless steel, there is a scoring system called from MOA that helps you determine which stainless steel might be appropriate. Stainless in the industry around the site over the last 50 years. So we had 3 coal-burning power plants, a coke plant, several steel mills, a copper mill, a zinc refinery, chemical plants, an ammunition plant that apparently managed to blow itself up on a somewhat regular basis. And there are remnants of them, and some still there. If we go back to the 1985 data from the National Atmospheric Deposition Program, unfortunately they didn't map it prior to that, but you can see acid rain was certainly part of the environment then. Now it's essentially disappearing, but it was a factor in the environment. So here are some GSR kits, and I'm showing how they're used by the police. And the ability to collect very fine particles. These are what some of those particles look like. You'll see the grays, browns, and kind of a little bit of a reddish tint. The top picture is at higher heights, as is the base with some of the streaking that is coming down from the welds. So we took these samples to an SEM and analyzed the particles. And here are a few pictures. The one shows iron oxide with a little bit of chlorides and some common soil contamination. The other is sodium chloride, obviously de-icing salt. But this summarizes what we found. There were very small amounts of de-icing salt and very minute levels, far too small to ever have picked up with anything but this type of test kit on most of the arch. But it's very, very small, which isn't surprising because of the highways. Higher concentrations, most of those deposits are fly ash, they're ferrochrome, and iron and steel slag, which are exactly what you would expect from coal-fired power plants, coke plant, steel mills, and which were in the area during the life. There were also some scattered iron particles, which you can get those from manufacturing sites, some copper and copper zinc. There is a copper mill. And lead, titanium, other things that match with the industry that has been in the area. And then a great deal of common soil constituents, clay, sand, etc., silica. This is what the base looked like, or still looks like. There is some very light superficial staining. I have a close-up picture of a very small pit. This is tiny. And this is all superficial, easily removed, absolutely no effect on structural integrity. There is some embedded carbon steel, both in the graffiti and there are these long lines at the base, which are probably from a plow or something similar. Those are probably the most deeply embedded. The that embedded iron really should be removed, at least from the deeper scratches, because you could continue to have some corrosion underneath it. These are the welds, or examples of some of the welds. They were all full penetration. As I mentioned, we had 5 samples, all 3/4 of an inch in diameter. There were no weld imperfections that caused any concern. Yes, there was some sensitization, which I'm showing a picture of here. Sensitization, when it causes corrosion, causes a classic band beside each side of the weld. Absolutely no evidence of that anywhere on the arch. If it hasn't occurred in the 50 years prior to this, when pollution levels were higher, then it's not going to occur in the future unless we have a dramatic change in the environment. So again, no concern. The welds, we did find records of them, of exactly what was done, including the cleaning. It was done prior to AWS D1.6, a structural welding code, but it was all done to boiler code requirements at the time. So again, no concerns about what was done. We did confirm that it was all 304, including the weld material. I did want to point out that there are a lot of resources if you're working with stainless steel, including those on your flash drive, and some conclusions. None of the weld imperfections are a concern. There were some, but nothing at all a problem. The weld sensitization has not caused corrosion. So again, no problems. The surface discoloration is superficial. It will have no effect. It's all from industrial pollutants. I think I made a joke once on site that you should send the carbon steel industry a bill, or maybe the power plants a bill. But you know, the cleaning would remove discoloration, but it is not needed. The only thing I thought should be removed was some of the embedded iron. Are there any questions?